2016 Junior Cert Higher Level question on trig, question 8. An unusual enough question. Part A, 1, write 2 degrees, 43 minutes, 5 seconds in degrees in decimal form, correct to 2 decimal place. So it doesn't come up that often, degrees in minutes, but does come up. So the button you're looking for on your calculator is this one. It's got a degree, and it's got a comma, and then it's got 2 commas. On mine, it's got an engineering button over it, and then under that is kind of the 7 and the 8. So that's where it's located on the calculator, okay? So this is your degrees and minutes buttons, okay? So when you're putting it into the calculator, go to and hit that button, and you'll see the little degree symbol coming up. Then hit 43 and hit that same button again, and you'll see another like a degree symbol coming up, a bit squarey, and then put in the 5 and hit the button again, and you'll see another kind of a little square button like that coming up, okay? And then hit equals, and it'll come up properly as 2 degrees, 43 minutes, 5 seconds, okay? So what you've done there is you've logged that angle into the calculator. If you hit this button again, you'll see it now switches between decimal degrees in decimal form, or if you keep hitting it, you'll go back to minutes and seconds. So what I'm getting there is 2.718 degrees. Now correct to 2 decimal places, I need to look at that one. That 8 is going to round that 1 before it up, because that 18 is closer to 20. So 2.72 degrees, that's 2 decimal places. So if it's to 2 decimal places, you're always looking at the 3rd place to see am I rounding up or leaving as is. Okay, now the same question but just in opposite form. So clear your calculator and I get 3.14 and hit equals. That just logs it into the calculator, and I'm getting 157 over 50. It's just after changing it to a fraction. Hit this button again, your degrees in minutes, and you see it now changing between 3.14 degrees and what I'm getting, which is 3 degrees, 8 minutes, 24 seconds. Okay, so how did I do that again? So 3.14, hit equals. You have to hit equals because that's the only way your Casio, your calculator knows that that's the full number, and you log it into the calculator and then hit this button here. Okay, so that's that question. The diagram shows a right-angled triangle with the angle A marked. Given that cos A is equal to sin A, show that the triangle must be isosceles. So this is an abstract question, quite difficult because it doesn't have numbers in it. Okay, but know that in any trig question, you're either looking at Pythagoras' theorems, this is the log tables, page 16, or sine, cos and tan. Those 4 little tools, if I can call them that, will solve any trig question that you get. Okay, so sine, cos, tan, Pythagoras' theorem. And because we're talking about angles A, you're not going to use Pythagoras' theorem because that's all about sides. Little c, little a, little b, all about sides. Okay, so Pythagoras' theorem, no good for this particular question, so it's sine, cos, tan. So however you remember these ratios, I'm silly old Harry caught a herring trawling off America. I might make that a little bit bigger because it's a bit of an eye chart there. So silly old Harry caught a heron trawling off America. Okay, and all they do is link relevant sides to sine, relevant sines to cos, relevant sines to tan. Okay, why am I doing this? Well, cos A is equal to sine A. Okay, so cos A is equal to sine A. Now we know that cos A is adjacent over hypotenuse. And we know that sine A is opposite over hypotenuse. Okay, so I haven't really done much there. I've written down what they gave me. I've put in this because it's the only thing I know about cos and sine, and I'm trying to see where does it bring me. Well, if the left equals the right, if cos is equal to sine, then adjacent over hypotenuse must be equal to opposite over hypotenuse. Well, obviously the hypotenuse are the same because it's the same side. Hypotenuse is always opposite the right angle. Therefore, then adjacent must be equal to the opposite side. Okay, so one of these sides is my adjacent. In fact, that's my opposite. That's my adjacent. How do I know that? Because opposite is always opposite the angle in the question. So my adjacent and my opposite are equal. Okay, and you know if two sides are equal in a triangle, therefore isosceles triangle. Okay, so quite a hard question because there was no numbers. Okay, part C, again quite unusual. A right angled triangle has sides of length 7, 24 and 25. Find the size of the smallest angle in the triangle. Okay, now do I have to find all three angles just to see which one is the smallest? Well, no, you don't. So it's a right angled triangle. So let me draw one. Okay, so 7, 24 and 25. Okay, well, it's a little bit of theory. Longest side in any right angled triangle is always your hypotenuse. It's always opposite the largest angle. And the largest angle in a right angle triangle is always the 90-degree one. Okay, in the same way, the smallest side, I don't know if it's going to be opposite or adjacent, but I know it will be opposite the smallest side. So that's a really handy piece of information to know when you get a question like this, because it means you don't have to calculate. Well, we know he's 90 degrees. We don't have to calculate both of these angles to figure out which one is the smallest. Okay, so we know the longest side is always the hypotenuse, which means my longest side is 25 here. Okay, now for the purpose of the diagram, it doesn't really matter which one I'll make 24 and 7. Okay, I'll just visually, that looks longer than the 7, so we'll make him 24 and the other one 7. So I have to work out the smallest angle. So the smallest angle is always opposite the smallest side. Okay, a bit hard to see that when I make it orange. Okay, that's my smallest angle and it's always opposite my smallest side. Okay, right, let me rub off the theory. So now it's on the recording anyway. If you want to go back and take it down, it's very useful to know. So how do I work out that angle up here? Well, it's an angle, so I can't use Pythagoras' theorem, so I'm using sin, cos or tan. Silly old Harry caught a herring trawling off America. Okay, and of course there's loads of rhymes. Oh hell, another hour of algebra is quite an easy one to remember. Okay, so my smallest side. Normally, so it doesn't matter if you use sin, cos or tan because that will work. All three will give you the same angle. Okay, and I might show you that in this question. Normally though, you've only enough information to be able to use one of them. But we're lucky enough in this question in that we have all three sides. So in theory, I can use any sin, cos or tan. Okay. So let's prove that we can use any. Well, let's use sine first. So if I can come up here, the sine of that angle is opposite over hypotenuse. Opposite, let's label our sides. This is opposite here. Side opposite, the right angle is your hypotenuse. So of course this is adjacent. So it's always opposite the angle in the question. Okay, so my opposite therefore then is 7 and my hypotenuse is 25. So sine theta is 7 over 25. I want theta the angle, not sine theta. So if I get sine inverse of both sides, that sine inverse cancels the sine. Okay, I want theta the angle. That's why I'm getting sine inverse. And you'll always use the inverse functions when you have to get an angle. So sine and sine inverse cancel. Why do I have to do it on this side? Well, what I do to one side of the equals to sine, I have to do to the other for balance. Okay, so that I'm getting theta being equal to the sine inverse of 7 over 25. So put that into your calculator. Sine inverse sits behind sine on the calculator. And I am getting an angle of 16.26 degrees for theta at the angle. Okay, so correct to one decimal place, 16.3 degrees. Okay, or I could have used cos. Cos is equal to, you'll see, adjacent over hypotenuse. So my adjacent side is 24, my hypotenuse is 25. The opposite of cos, because again I want to get at theta the angle, opposite of cos is cos inverse. So I get the cos inverse of both sides. Cos and cos inverse cancel to leave me with theta, the angle, being equal to cos inverse of 24 over 25. So put that into your calculator. Cos inverse lives behind cos, and you'll see you get theta being equal to 16.26 degrees again, or theta being equal to 16.3. Or you could have used tan. Tan theta, though, the sides that tan links together are opposite over adjacent. You can see these just link different sides together. So tan is opposite, so 7 over 24. Opposite over adjacent. I want theta the angle, so I have to get rid of tan. So the opposite of tan is tan inverse. So theta then is equal to the tan inverse of 7 over 24. Tan inverse sits behind tan, and you get 16.26 again, or 16.3 degrees. Okay, so just to recap on that question, it gave us 3 sides. I just drew a triangle to represent it. Always know that the smallest angle is opposite the smallest side. That's how I knew a smallest angle was going to be that one. That's 90 degrees. If I were to work out this one now, I would add 90 and 16.3 and subtract from 180. Okay? Because I had all 3 sides, I could have used sine or cos or tan. You don't have to do all 3, you just pick whichever one you want to give you that angle, that smallest angle being 16.3 degrees. Okay, and that was the 2016 question.